Hello children, this is Karthik from a physics faculty from Perfect Academy. So today we are going to discuss some important aspects of the magnetic effects of current. First of all, let us know how to find out the magnetic field intensity due to any configuration. And for finding the magnetic field intensity, we have two important tools. One is Ampere circuit law, another one is Biotsavart law. Biotsavart law is for finding the magnetic field intensity due to a straight conductor. It may be like a straight conductor, or it may be like arc, or it may be like any kind of structure, any kind of configuration. And Ampere circuit law is for finding the magnetic field intensity of any symmetric arrangement, like a magnetic field intensity due to solenoid, magnetic field intensity due to toroid, magnetic field intensity due to a thick conductor at different points. One is outside, inside, all the things we will see. We will cover all those things. Now, let me start with the Biotsavart law. Actually, the Biotsavart law is given for Biotsavart law. Actually, he has given this formula for finding the magnetic field intensity due to a moving charge. So, let us suppose this is the charge Q and it is moving in the space with a velocity V as shown like this. And let us suppose this is the point P, some reference point. Through this point it is moving in the space with a velocity V. I would like to find out some point here which I would like to call as a Q. I would like to find out what is the magnetic field intensity due to this moving charge that moving with a velocity V at this point Q. Now let me draw one reference line, what we are calling as a position vector of Q with respect to P. And so this is going to be R bar and its length is nothing but R. And here the velocity direction is like this. Here I have drawn one parallel vector. So let us suppose the angle between these two equals to phi. And this velocity can be resolved into two components. One is V cos pi, another one is the V sin pi. So this is going to be the velocity component V sin phi. And now, according to Biotsavart law, the magnetic field intensity at this point Q is directly proportional to the charge Q and directly proportional to the V sin phi and inversely proportional to R square. So by combining all this, we will write like this. The magnetic field intensity, magnetic field intensity B is directly proportional to Q and inversely proportional to, directly proportional to V sin phi, inversely proportional to R square. By combining all this, let me try to frame one relation here, that is nothing but mu naught by 4 pi times of Q V sin phi divided by R square. Actually, this is the Biotsavart law. Initially it has given for this one, for moving charged particle only, but it can be modified for a straight line conductor. So this is nothing but basically magnitude, but if I would like to write magnetic field intensity in its vector form, then I have to write like this, mu naught by 4 pi times of Q into V bar cross R cap divided by R square, where R cap is nothing but unit vector of the line joining P to Q. So this is nothing but R bar, that's what we understood, R bar, and it can be written as R into R cap. That unit vector only I have denoted here. Now let me modify this expression for our straight conductor, and that's what you people know that. And so let me try to modify this. The Biotsavart law for a conductor which is carrying the current I. So here, let us suppose it is a one conductor which is irregular in shape, it's not a straight conductor, and there is a one point P here, and this conductor is carrying the current I. So let me choose one small element here, and which is having the length of L, and this length vector, this length of the element is nothing but basically vector quantity whose direction is towards the current flow. So this is a length element which is a vector quantity dl bar, and so this point P is at a distance of R, so that I can call the position vector of P as in R bar, and the both are subtending an angle of phi between them. Now see here, what is the length of the element? The length of the element is nothing but how much? As I told you there, dl is going to be length of the element. Then if A is the area of the cross section, then what is going to be the volume of the element? Volume of the element. This could be written as, if I know the area of cross section and if we know the length, the product is nothing but volume of the element. Let us suppose small n is nothing but number of charge carriers available per unit volume in this conductor. Now, what is the total number of charge carriers available now in this small element? Total number of charge carriers. I am writing just charge carriers only. The total number of charge carriers, that is nothing but ADL multiplied by N. This is going to be the total number of charge carriers. Now, what's the total charge? The total charge, this can be written as NaDl multiplied by the E, where E is nothing but the charge on the electron. Now this is nothing but the total charge. And what is their velocity? Inside the conductor, they will move with a velocity called drift velocity. That we know, and that's what the velocity of this total charge is nothing but Vd. And from the Biotsavart Law original form, what we know, B magnitude is nothing but mu naught by 4 pi times of Q B sin phi divided by R square. Now I would like to substitute back the information what I know to this expression. Well, mu naught by 4 pi times of, what's the Q? Q is nothing but the total charge. This is the total charge. NeADL multiplied by the V is nothing but velocity of that charge, and that is nothing but drift velocity, and that is multiplied by sin phi whole divided by R square. We know very well from the current electricity topic, the relationship between the current and the drift velocity is nothing but I equals to NeAVd. The same thing I would like to take back to here. So I can rewrite this expression like this: mu naught by 4 pi times of IDL sin theta divided by R square. Here I have written phi, so let me rewrite this: sin phi. So magnetic field intensity at any point due to a current element of straight conductor, or like it is like irregular shape. So due to any current element, the magnetic field intensity at a point P is given by mu naught by 4 pi times of IDL sin phi divided by R square. This is the magnetic field intensity magnitude. Now let us speak about the direction of a magnetic field. The direction of a magnetic field is given by right thumb rule. What is the right thumb rule? If I stretch my thumb in the direction of flow of current, then the direction in which the fingers are curling about that point, that will be the direction of a magnetic field. For example, here I have the current is going from here to here, therefore I can stretch my finger like this, the thumb. Now the remaining fingers has to curl into this point P, and it has to come out from this side. The fingers has to curl into and come out from this side. So here the direction of magnetic field is nothing but into, because my fingers are curling into. If the same point P is available here at the same distances, then here the direction of magnetic field will be out. This will be out, because here the fingers will be curl out of this point. Therefore the direction of magnetic field, here it will be out, here it will be into. Now the same right thumb rule can be modified for a circular shaped conductor, not exclusively for circular shaped conductor. For any kind of shape of a conductor, we can tell what is the direction of a magnetic field by slightly modifying this right thumb rule. So let us see what is that. So if I have let me take one simple example here. So here I have two conductors which are one is like this, carrying the current I in clockwise direction, and there is another loop which is carrying the current in anti-clockwise direction, and there is one point here, let me call it as a center, and therefore here somewhere the point P is like inside it. Now I would like to find out what is the direction of a magnetic field. Now as I told you, the right thumb rule can be slightly modified for this kind of a closed loops. How it is? So if the current is going like this, then I mean either clockwise or anti-clockwise, let it be. Here the current is going in clockwise. Now I have to curl the fingers in the clockwise direction. Then my thumb will either move into or out of this plane. So here the current is going like this. Therefore I have to curl my fingers in this direction. The thumb is showing into the plane of a board. Therefore at the point C, the direction of magnetic field is into. And let us come to here. Here it is like not a pure circular loop. It is some irregular shape. Let it be. So here the current is going like this. Now the thumb is stretching out. That means from out of the plane of the board. Therefore magnetic field intensity at this point due to this loop will be out of this plane of board. This is the direction of a magnetic field. This is what about the magnitude of magnetic field intensity that can be found from Biotsavart law, and these two are the informations for the direction of a magnetic field. And let us see some applications of important applications of the Biotsavart law. Well, so we will start here now with the applications of Biotsavart law. Applications of Biotsavart law. What are the applications? We will begin now by writing the formula for the magnetic field intensity due to straight conductor. So these are all we have done for irregular shaped conductor. Now I am going to tell you the formula for straight conductor. A straight conductor. Let us see. So here I am not going to give you any kind of derivations, but a simple formula and how to use them, that alone I will discuss here. And let us suppose this is a one straight conductor and there is a one point P here which is at a perpendicular distance from the straight conductor of A. Here is a point P that is lying at a perpendicular distance of A from the straight conductor, and the adherents of a conductor are subtending an angles of alpha and beta respectively. The adherents are subtending an angles of alpha and beta respectively by the point P. And now the magnetic field intensity at the point P, magnitude alone I am writing. So this is going to be equals to, let us suppose it is carrying the current I, and from down to top, let it be. Then what is the magnitude? That is given by mu naught I by 4 pi A times of sine alpha plus sine beta. And from this expression, we can make two important conclusions. One is that, conclusion number one. For, let us suppose I would like to find out the magnetic field intensity due to infinitely long conductor. Infinitely long conductor. So what is the meaning of infinitely long conductor? Let us suppose if I write one conductor like this. So there is a one lengthy conductor whose ends cannot be shown on this diagram. Then this kind of conductor will be called as an infinitely long conductor, and which is carrying the current I, and let us suppose here is a point P and which is at a perpendicular distance of A as I have written there. And now what is the magnetic field intensity at this point P? So for this finitely long conductor, I have angles alpha and beta which are subtending at adherents. And for this case, the same alpha and beta are going to be equals to 90 degrees. Because it's infinitely long, and the point P will subtend an angle of 90 degrees and 90 degrees on either sides. Then by substituting this information back to this expression, we will get the magnetic field intensity magnitude as a mu naught I divided by 2 pi A. This is the magnetic field intensity due to infinitely long conductor. Now let us rewrite the, I told you here we have the two important implications. One is that infinite long conductor and another one is semi-infinitely long conductor. Semi-infinitely long. What is the meaning of this semi-infinitely long? So it is nothing but basically infinitely long conductor only. But the point P, which is at a perpendicular distance of A, lies near to one of the end. Here, somewhere on its length, the point P is lying perpendicularly from the conductor. Whereas here, the point P is lying at nearby the one of the end. Nearby one of the end. The other end is continuing like this. And now for this case, what is going to be the alpha? Alpha is going to be 0 degrees and beta is going to be equals to 90 degrees. By substituting this information back to our Biotsavart law, and we will get the magnetic field intensity magnitude as a mu naught I divided by 4 pi A. Because sin beta equals to 1 and sin alpha is going to become 0. Therefore, we will get magnitude of magnetic field intensity as a mu naught I by 4 pi A due to semi-infinitely long conductor. Done. And this is what about the straight conductors. Now let us speak about arc-shaped conductor. Sorry. Let us see that the second application of this Biotsavart law, that is arc-shaped conductor. Arc-shaped conductor. Well, so due to an arc-shaped conductor, let us suppose it is carrying the current I, and somewhere here the center is lying, and the radius of this arc is nothing but r, and let us suppose here the angle is nothing but alpha. Then what is the magnetic field intensity due to this arc at the point C, I mean at the center? That is nothing but magnitude of magnetic field intensity is given by the formula mu naught I divided by 4 pi r into alpha. Mu naught I by 4 pi r multiplied by alpha, where alpha is measured in units of radians. If it is a semicircular shaped conductor, then alpha is going to be pi radians. That's what if you substitute back, you will be get magnitude of magnetic field intensity as a mu naught I divided by 4r. If it is like a complete circular shaped loop, if it is a semicircular, alpha is going to be 5. If it is like a complete circle, alpha is going to be equals to 2 pi. And we know the magnetic field intensity at the center of a circular shaped conductor is nothing but mu naught I divided by 2r. Mu naught I divided by 2r. This is going to be the magnetic field intensity due to the circular shaped conductor. Now, let us see what is the direction of magnetic field intensity at the center C. I already told you the right thumb rule can be modified slightly for writing the direction of magnetic field intensity due to a arc shaped or any kind of loop shaped conductors and loop conductors. And here the current is going like this clockwise, therefore I have to curl my fingers along the clockwise direction, then thumb is showing into the plane of a board. Therefore at this point C, the direction of magnetic field is into. The direction of magnetic field is intensity is into. This is what. And so this is so far we understood about Biotsavart Law and applications for the straight conductor, infinitely long, semi-infinitely, and here it is arc shaped and semi-circular, finally circular shaped conductor. Now let me give you one more formula related to this circular shaped conductor. So generally for a circular shaped conductor, if the point P is lying on its axial line, what is the meaning of axial line? So let us suppose on the axial line of circular loop or circular shaped conductor. So here I am assuming this is a circular loop which is carrying the current I like this, and it has a radius equals to a, and from the center there is one axis going through and normal to the plane of a loop. So let us suppose if the loop is like this, the axial line is going like this. Now this is going to be axial line, and there is one point P here which is at a distance of x away from the center. Then at this point the magnetic field intensity magnitude is given by the formula, that it will be given by the formula mu naught I times of a square divided by 2 into a square plus x square whole power 3 by 2. This is the formula mu naught I a square divided by 2 into a square plus x square whole power 3 by 2. So here if you substitute x equals to 0, you will be left with mu naught I a square divided by 2a cube, which will give the previous result mu naught I divided by 2a. That is nothing but the magnetic field intensity due to the circular shaped loop, I mean the loop at the center, circular shaped loop at the center. We know that formula. Same thing we are going to obtain from this result also. Now at the point P, what is the direction of a magnetic field intensity? As I told you, this is nothing but the loop that can be shown like here. So it is carrying the current like this. That means it is going the current like this. Now this will be the direction of a magnetic field intensity. Now we know if it is going into means into will keep, and if the magnetic field is out means we will keep the dot. Now how to show like this? Every time we cannot show like this. So we will make the use of XYZ axis system. That means the magnetic field intensity at this point P, let us suppose it is along the positive x-axis. Then this can be written as, if I want to write vectorially, the magnetic field intensity equals to mu naught I a square by 2 into a square plus x square whole power 3 by 2 multiplied by I cap, because magnetic field intensity is along the positive x-axis. So hereafter, when we have any kind of arrangement which is pertaining to any kind of planes. There we will make the use of unit vectors for writing the direction of magnetic field intensities. This is what briefly the magnetic field intensity due to different arrangements. Now let us look at some illustration to better understand how to apply the known formulas. We will go with some illustrations now. Well, so let me begin with a very simple illustration where I have a conductor carrying the current that's bent at the middle somewhere here, and it's continuing to be like this. Now, from the center, the radius is nothing but r, let us suppose. Then I would like to find out what is the magnetic field intensity at the point C due to this arrangement. Here, totally 3 subparts are there. One is this, another one is this one, the third one is this one. And this point C is lying on the extended line of a conductor, whereas the same point C is lying on the extended line of a second conductor also. Whenever the point P or point C is lying on the extended line of a conductor, straight conductor, there the magnetic field intensity will be 0, because we know from the Biotsavart Law what is the magnetic field intensity? Mu naught IDL sin theta or sin phi 4 pi r square, where phi is nothing but angle between the position vector and the current element. So this is what I have drawn there, and this is going to be the dl direction. This is the point P and its position vector is r bar. Now let me take this point P onto the extended line of this conductor somewhere like this. The point P I have shifted to here. Of course, at the same position vector r bar only. But in this case, the angle between dl bar and r bar is nothing but 0 degrees. And that's what if we substitute back sin 0, 0. So magnetic field intensity is going to be 0. Therefore, whenever the point P is lying on the extended line of a conductor, there that on that point, magnetic field intensity will be 0. The same thing I am going to apply here. So for this point, for this conductor, this point is lying on the extended line. Therefore, due to this, at this point, magnetic field intensity will be 0. Even due to this also, magnetic intensity will be 0. Therefore, I could able to obtain the magnetic field intensity due to this semicircular arc only. Therefore, what is the magnetic field intensity due to it? We know very well. Magnitude is given by mu naught I divided by 4r, because it is a semicircular. And what is the direction? So here I can apply my right thumb rule. What is that? If I curl my fingers in the direction of a current, the thumb is showing into the plane of a board. Therefore, this is into. This is the one of the simplest application, one of the simplest illustration. Now let us move for the second illustration. So here we have illustration 2. Illustration 2. So what is that second illustration? We have like this. So let us suppose there is a one infinitely long conductor which is make like this. So it is a circular shaped conductor. I mean somewhere at the middle it is bent like a circular shape, and whose radius is r. And this is the center C. I would like to find out what is the magnetic field intensity due to this configuration at the point C. This is what our task. Now here also we have the 2 parts. One is that infinitely long conductor, another one is circular shaped conductor. Due to the infinitely long conductor at some perpendicular distance, what is the magnetic field intensity? Mu naught I divided by 2 pi a. This is what we know. Mu naught I divided by 2 pi a. This is the magnetic field intensity due to the infinitely long conductor. Here that a is nothing but r, and it is carrying the current I, let me assume. Therefore, due to this, what is the magnetic field intensity? Shall I call it as a conductor 1? It is a conductor 2. Therefore, the magnetic field intensity due to the first conductor, which is nothing but infinitely long, is given by the formula mu naught I divided by 2 pi a. And what is the direction? Since it is carrying the current like this, so I can stretch my thumb like this because it's a straight conductor, and I have to curl my fingers which are coming out of the point C. Therefore, the direction will be out. And let me speak about the conductor 2. It is circular in shape, and it's a complete circle. Therefore, what is the magnetic field intensity? Since I have drawn the direction here, I could keep here vector sign. Now, what is the B2? B2 is going to becomes mu naught I divided by, it's a complete circle, therefore 2r. And what is the direction? Let me curl my fingers like this because it's a circular loop and the thumb is showing out, therefore out. And both are in the same direction. Therefore, what is the net magnetic field? The net magnetic field is given by B1 bar plus B2 bar, which will give the result mu naught I divided by 2 times of 1 by pi a plus 1 by r, and totally out. This is the direction of a magnetic field intensity and magnitude of resultant. And this is how this problem will work out. And let us see the third application of this third illustration. Let us see that a third illustration. Let us see what is that. So here I have one conductor, and here I have a center C, and this is the radius, and there is one conductor which is being continuing like this. It's carrying the current in this way and it's been continuing like here, and here there is one arc shaped conductor, straight conductor, and it's also straight conductor. Now at the point C, I would like to find out what is the magnetic field intensity. First of all, how many conductors are there? Here totally 3 parts are there. One is infinitely long, such that the point C is lying at one of the end. Therefore, it can be considered as a semi-infinitely long conductor. The second one is arc-shaped conductor. The third one is infinitely long, but the point C is lying on the extended line. Therefore, due to this, there will be no magnetic field intensity. And so, let me go on with calculation of these two. So, due to this infinitely long and where the point C is lying nearby one of the end, what is the magnetic field intensity? I know very well. The formula could be written as mu naught I divided by 4 pi a. That a is here nothing but radius. What is the direction? Since the thumb has to stretch like this, the fingers has to curl into. Therefore, the direction of magnetic field is into. And shall I call it as a conductor 1? Therefore, B1 is going to be the magnetic field intensity. Now, what about this part? It is an arc and it should subtend some angle at the center. What is that angle? This angle is 90 degrees. Therefore, this whole angle will be how much? 2 pi minus pi by 2. How much it is? 3 pi by 2. That is the angle subtended by this arc. And what could be the magnetic field intensity? That will be equals to mu naught I divided by 4 pi r times of alpha. Alpha is nothing but here 3 pi by 2 radians. And further, let me cancel all. What I will get? 3 mu naught I divided by 8r. What is the direction? The direction is given by, since it is carrying the current like this, it is carrying the current like this, therefore into. So here it is also again into. Since the both are in the same direction, the net magnetic field is nothing but B1 bar plus B2 bar. And what is going to be the result? Mu naught I divided by 4r is nothing but 3 by 2 plus 1 by pi. This is going to be the result, the net magnetic field intensity. Some more illustrations will continue in the next session. Thank you.